Welcome everyone. Today I will be talking about LegRoast, our efficient post-quantum signatures from the Legendre PRF. This is joint work with Ward Beullens, and I am Cyprien Delpech de Guilhem. Together we work at the IMEC COSEC group in KU Leuven. If you are interested in the entire paper, the preprint is available at this ePrint number. So to give an introduction of MPC-in-the-head signatures, the current main proposal for these kind of signatures is the picnic scheme. And the main idea behind this is that we take a one-way function and we turn it into a signature scheme. So the security in some sense is that the private key relies on the knowledge of a pre-image of the one-way function. And the public key is the corresponding image, of course. The picnic case, they use the low MC block cipher, and you can see on the graph that for a certain, if you spend a certain amount of time, you get a certain signature size, and if you work a little bit harder, you can reduce the size of your signature by more than half. In our work, we investigate different primitives to use as the one-way function, namely, first of all, the Legendre PRF, which gives us the LegRoast signature scheme. And you can see on the graph that already for comparable signature time, we have reduced the size quite a lot. And if we actually use the power residue pseudo-random function, which gives us the pork roast signature scheme, we can reduce not only the size even more, but even the speed. As in, we increase the speed. So to get into some more details, first I will explain a bit what MPC-in-the-head signatures are. Then I will describe the Legendre PRF and its companion, the higher power order PRF. And finally, I will describe the optimizations that we bring in this context to produce the LegRoast and pork roast signature schemes. So the idea of MPC-in-the-head signatures is that you provide a zero knowledge proof of knowledge of a secret key K, a secret symmetric key. So in the case of the low MC block cipher, the secret key of the signature scheme is a random key, and the public key is a plaintext ciphertext pair. So we've labeled them M and C here. And to sign a message, we produce a zero knowledge proof that we know the key K that links the plaintext to the ciphertext in the public key. And to make it a signature scheme, we inject the message that needs to be signed into this zero knowledge proof. For the verification, it's pretty much the opposite. You verify the zero knowledge proof by inserting the same message that you're supposed to verify the signature for. So we have a little diagram representation here. The secret witness is this secret key K, and the public parameters are the plaintext M and the ciphertext that come out. And this is the little schematic proof of knowledge. MPC-in-the-head is a way of constructing such a proof of knowledge. The idea here is that the prover Alice, here on the left, will simulate an MPC protocol in her own head. So we have these little parties in her head who are computing the encryption scheme. And Bob, on the other side, will challenge her on this simulation to verify that she did it correctly. And the idea is that the properties, the security properties of the MPC protocol will mean that Alice will have a very small probability of cheating if she doesn't actually know the correct witness. To describe the flows quickly, in the first round, Alice commits to some pre-processing data. Bob will challenge her to open all but one of them to verify that she has computed this pre-processing correctly. So if she's done it on all but one of them correctly, and obviously the last one that she doesn't reveal is randomly chosen, then the probability that she did it correctly for that one is quite high as well. Using this pre-processing data, Alice then executes this MPC protocol and saves the view of each party. She then commits to these, and Bob, the verifier, will challenge her to observe all but one of these views. And if he sees that all of these parties behaved honestly in Alice's simulation, then he will accept. The idea here is that if she didn't know a witness, Alice would have to cheat in the execution of the MPC protocol so that the result would still be valid. By only letting her have one party to hide behind, which is of course chosen at random, Bob is fairly certain that Alice did not cheat on the last party as well, because he can observe all the others. And then he obtains guarantees that Alice did really know the witness. The most important thing to remember for our purposes is that the proof size is going to be proportional to the number of multiplications or AND gates in binary circuits, which LowMC has a certain number of. And that's what we're trying to reduce here. So now to give an introduction and a description of the Legendre PRF. We first talk about the Legendre symbol. In and of itself, the Legendre symbol is an indicator of whether a certain number A is a prime modulo, is a square, sorry, modulo an odd prime P. So by looking at this exponentiation a to the p minus 1 over 2, we know that this is 0 if A is divisible by P, 1 if A is a square modulo P, and minus 1 if A is not. Now, the interesting thing here is that if we take the sequence of Legendre symbol from 1 to p minus 1, then this behaves almost like a uniformly random sequence of ones and minus ones, which can just be translated to ones and zeros, therefore bits. So each sequence of length n, for example, appears approximately p over 2 to the n time, which means that it's a good source of randomness. Now, it was even Damgaard's idea to use this as an actual PRF for cryptographic purposes. So by choosing a key k modulo p, the PRF is then to evaluate the Legendre symbol of an integer a shifted by k. So this produces one symbol, one bit of output, and by extension, you can take a sequence of a plus k, and then the next one, the next two, and so on and so on. Looking at cryptanalysis results of the Legendre PRF, we see that if given quantum access to the PRF, so the adversary is allowed to query PRF evaluations in superposition, then the attack is polynomial time. In classical access, the attack runs in square root of p time. But here we have to remember that for the MPC-in-the-head setting, the key pair is only one instance of pre-image image for the case of the one-way function assumption. So in the case of LowMC, we had a secret key k, but the public key contained only one plaintext ciphertext pair. So the adversary doesn't actually have oracle access to the one-way function. They only have the one query of the public key, and they cannot even adapt it to what they want. For our case, only one symbol is not enough of the Legendre PRF, but we will have a few, but not too many. So therefore, we consider the cryptanalysis of the PRF in the case where the number of queries is restricted. So when an adversary can make less than square root of p sequential symbol computation, then the complexity then moves to p over m squared. And in fact, if we only allow about log p random symbols to be given to the adversary, then we actually achieve an attack complexity of order of p. And this is the setting that we aim for to ensure that our one-way function assumption on the Legendre PRF remains valid. The power residue pseudo-random function comes from generalizing the Legendre symbol, which indicates whether an integer is a square or not modulo p, to higher powers. So in this case, we have the operation we can see on the right, exponentiation by p to the minus 1 over k, which gives a range of value between 0 and k modulo p, which indicates whether a is a kth power or not. And then we can derive a PRF in the same way, with the key providing a shift to the input and the function just evaluating the symbol. So we note that here each symbol provides more than one bit of output depending on the size of k. So it's a bit more efficient as well. In this case, the cryptanalysis is the same, except that there is a slight advantage to be gained in the final case, which is our setting, and the attack complexity is reduced from order of p to order of p over k. So depending on our choice of k, sometimes we need to increase p slightly to ensure we achieve the same security level. So finally, because for the MPC-in-the-head paradigm, the MPC protocol that the prover will simulate or the signer will simulate has to compute this function, we have to look at how to compute the Legendre symbol in MPC. The very naive way is to do it the long way, which is to use the reciprocity properties of the symbol, and instead of computing the symbol of A modulo P, we compute the symbol of P modulo A, and we go down the chain like this. But this is expensive, and there's an easier way to do it, which is that parties, first of all, sample a random value R, which has to be non-zero, and then they compute the multiplication AR squared. So that takes 2 multiplications because we need to square R. Then they reveal this value AR square, and we know that this doesn't leak any information about A because R is perfectly random, except if A was 0, but we prevent for that case. And the only thing it can reveal is the Legendre symbol of A, but this is what we're trying to prove, so it's not actually a problem. Then the parties can compute the Legendre symbol of AR squared modulo P in the clear. And because the Legendre symbol is multiplicative, and that the Legendre symbol of a square is 1, then this results in exactly the Legendre symbol of A. So this is quite an efficient way of computing such a symbol. Only 2 multiplications in the MPC protocol are required. So now we use this optimization within our the MPC-in-the-head paradigm, and we present a couple more optimizations as well. So, as I was just saying, can we improve the efficiency? And in fact, I kind of spoiled it for you all because the graphs at the beginning says, yes, we can. So the first attempt was we select a secret key K, like in the low MC case, and the public key is just a sequence of Legendre symbol. So essentially we're evaluating the Legendre PRF at 0, shifted by K, and we publish the lambda symbols that follow from this value. Now, if we return to our schema a little bit, we can see that the K is inserted into the MPC proving engine, and this one outputs the lambda Legendre symbols. Now, as we said before, computing the whole Legendre symbol is not efficient, and computing lambda of them is even less efficient. Furthermore, this process has to be repeated in parallel several times to increase the soundness to a desirable level. So this first attempt is not the best. Instead, what we say is that we randomly choose a set I of indices little I. Then when computing a public key, we publish this set, and we also publish the symbols, so each I shifted by K. So instead of having a sequence of symbols, we just have a set of random symbols, each shifted by this key. Then we have to increase the rounds of the protocol to gain efficiency so that the prover can commit to his input, at which point he has to commit to the secret key K that he's going to prove. And the verifier then selects a small number of these random symbols, namely B. And typically B won't be more than 15 or 20, even though big I could be 4,000, if not more. Then the prover engages in this MPC-in-the-head protocol to compute the Legendre symbols only of the indices that the verifier chose at random. So by making this challenge probabilistic, we can choose much less symbols and therefore reduce the cost to the MPC protocol. Here this time we have the inputs coming, the indices coming as a public challenge. And we note that also here we add this R squared trick that we mentioned earlier, so that the MPC-in-the-head does not actually compute the Legendre symbols, but it just computes these B multiplications. And then it's the verifier's role to compute those Legendre symbols in the clear. But because verifier doesn't have to do it distributed across many parties, this is actually much more efficient because the prover would have to do it across many parties. So to analyze what could go wrong here, we first note that the prover could guess which party is going to remain hidden in the MPC-in-the-head part. So he's got a probability of 1 over n to choose this correctly. If he does, then he can get away with cheating. But with an appropriate choice for n, this happens rarely. The second strategy is to use a wrong witness, a wrong secret key k prime, and to hope that it will align itself on the randomly chosen symbols by the verifier. But note first that the prover has to commit to his choice of key before he can see the symbols. So he cannot choose an alternative witness after knowing which symbols he's going to be tested on. And we analyzed that if the Legendre symbols agree for a certain fraction beta of the indices, then quite simply, the cheating probability will be beta to the b, because each random index has to agree. But by the veil bound, we know that if a is large enough, then this fraction of beta is about a half, or maybe just a bit more, for any other value of k. So the cheating probability in the second phase is actually 2 to the minus b. And if the prover is in fact able to find a key that agrees on almost all of the symbols, then in fact he has found the real key anyway. So these are the main two optimizations that we presented, namely not computing the Legendre symbol in the MPC protocol, only computing multiplications, and challenging only a random subset of symbols. But we have further optimizations as well. Namely, we can reduce first to only one multiplication per Legendre symbol. Then we can also batch all of the B multiplications into a single verification check, which means we reduce further the number of multiplications. Then we can also make use of the power residue pseudo-random function that I introduced instead of the Legendre one. And because of the increased size of the output and some of the increased security properties, this allows us for more gains in efficiency. And also to optimize the arithmetic, we can select the Mersenne prime 2 to the 127 minus 1 as a good option. So summarizing the parameter set here, we see that we choose 64 parties for both cases. And this was in line with the Picnic 2 recommendation. The Picnic 3 recommendation has now moved to only using 16 parties, but in the paper we provided 64. The parameter M is the number of parallel executions of the proof that has to be done so that the soundness is satisfactory. And B, as before, is the number of symbols that we check. So typically we choose a proof size of about 4 kilobytes. So there's quite a few Legendre symbols. And you see that for pork roast, we actually only verify 5 of them. But our soundness analysis shows that this is enough to achieve a negligible probability of cheating. Finally, we can see here that the signature size are much smaller and the signing time are also very efficient. So finally, to conclude, we've shown that the Legendre PRF or its generalization, the power residue PRF, are both more efficient alternatives to low MC as a basis for MPC-in-the-head signatures. The question is, are they just as safe, safer, not more weak? It's hard to know. So the open questions is, first of all, better cryptanalysis of these pseudo-random functions. Not only in the general case, where the adversary can make multiple queries, but in the low data setting, where only few queries and maybe fixed queries are allowed, and also in the case where the prime is of a particular form. Then we can always ask the question, can we optimize our scheme further, and can we implement it faster? But these we'll have to leave for further work. So thank you for listening to this video. I will be available to take some questions. And if you don't get the chance, you're always welcome to email me or my colleague Wart at the details that can be found on our groups page or on the ePrint paper. Thank you very much.